Let's continue our discussion of recursion with a recursive method to figure out whether a word's a palindrome, the same backwards and forwards. And let's look at how we might do this by hand. If we want to find out if the word rotor is a palindrome, we'll look at the first and last characters. And if they match, then we get rid of them and look at what's left. And then we ask, is that a palindrome? And we repeat the same process. We look at the first and last characters. If they match, we get rid of them. And now we're down to one character and ask, is that a palindrome? Well, if there's only one character, it has to be the same backwards as forwards. And the answer is yes. If at any point the last and first characters didn't match, we'd be done. We wouldn't have to go any further because a mismatch means it's not a palindrome. So that's the general flow of what we want to do in Java to solve this problem. Notice at each stage I have the full word, then a smaller word, then a smaller word or part of a word until I get down to one character or 0 characters. For example, the word noon, N-O-O-N, is a palindrome, and when you get rid of the 2 N's and get rid of the 2 O's, there's nothing left. And here is the method. If the length of the word is less than or equal to 1, then it's a palindrome. Otherwise, check to see if the first character and the last character are the same. If they are, then take the substring from 1 up to but not including the last character and see if that's a palindrome. There's our recursive call. If there's a mismatch, I can return false immediately. There's no point in going further. Now let's see what happens when I call this isPal method with the word rotor. We open up a new stack frame with S containing that string. Because the length is greater than 1, we're going to look at the last and first characters, and since they are the same, we'll look at the rest of the string without those characters, and now we have to return isPal of that string, the rest, which is OTO. There's our recursive call. We open up a new stack frame. Now S is OTO. The length is greater than 1. We check the first and last character. They're the same. Get rid of them, and what's left over is the letter T. And now we're going to do another recursive call to say, okay, is that a palindrome? A new stack frame opens up, and we have the letter T as our string. Its length is less than or equal to 1, and we're going to return true. The return will return the value and it will get rid of the stack frame. Now we're back to where we called it with OTO, and we are going to return whether it's a palindrome. We know it's a true, and so the true gets passed back one level up, which brings us back to the first call to isPal, and then that gets returned and passed back to main, and the result is set to true. What's happening here is that the true value gets passed up the chain unchanged. What's happening is that the true gets passed all the way down the chain to the main method. Because it's the same value being passed, you can think of it as if the true value from our base case went directly back to the main method. The reason that this recursive method happens to work this way is because it is tail recursive. And a method is called tail recursive when the recursive call comes as the last operation in the method. So here, the last operation that we did before returning was calling the method recursively. This is unlike what we did in the previous lecture, where I was trying to find the sum of a list of integers. In this case, the last operation that was done when we returned was the addition, not the recursive call. So here's what the call stack looks like for our tail recursion, and again, it's as if we can shortcut it and return it all the way to the top. Now it turns out that there's something called tail call optimization, and some languages, although Java's not one of them, will work that way. They will simplify the call structure so that they use only one call frame and reuse it over and over and over again, and you will never have a stack overflow. And again, the reason they can do it is because the recursive call is the very last operation in the method. That won't work here in our list sum method because it's a different value being passed up at each stage when we return, and it's a different value because the recursive call wasn't the very last thing. It was the addition. Now, the next question is there a way to make our list sum a tail recursive method? And the answer is yes. We're going to pull a trick that I call the accumulator trick. When we have our method, we're going to have the recursive method, and we are going to have two parameters, the head of the list, and we're also going to keep the total and pass that on from one call to the next. If the head is null, we're done, we've hit the base case, and we can return the total. If the head isn't null, then the last thing we're going to do is our recursive call. We're going to call the sum method with the next item in the list and the current total plus whatever we were looking at. So the trick here is to accumulate the total by passing it on as another parameter in our recursive call. So let's look at what's happening here. We're going to do the sum of list.getHead, and the initial value of our total is 0. On our first call, the head will be 5, and our total will be 0. That's not null, which means we're going to call sum again with get next of head, that's the 3, and total, which is 0 plus head.getData, and that works out to 5. In our next stack frame, we have 3 as the head, 5 as the total. That isn't null, so we return the sum starting at the next item, 7, with an accumulated total of 5, which was our old total, plus 3. That opens up a new stack frame. Our head is 7, the total was 8. That isn't null. And so we'll call sum again, this time with the next item after the 7, which is the null entry, the end of our list. And the current total, which is 8 plus the 7, which gives us 15. And now here we are, the head is null, the total is 15. Because the head is equal to null, we're now going to return the total, which returns the 15 and gets rid of the stack frame. That will return the 15 and get rid of the stack frame. Returns the 15 again, gets rid of that stack frame. And finally, our first call within main returns the 15. And now we have a tail recursive method for doing the sum by keeping our result and passing it along as one of the parameters in the recursive call. And that allows us to make the recursive call the very last thing.